All right, guys. So let's get started. So we have we're going to sort of continue carbonyl chapter today. Last week we kind of introduced it in terms of understanding the electrophilic nature of carbonyls, and so we saw, for example, reduction chemistry, which is in essence just hydride addition, right? And we also saw that you can apply this to Grignards and so forth. We saw the impact that they can have on esters. Within reductions, we, for example, mentioned lithium aluminum hydride and sodium borohydride. Recognize that not only is there a relative reactivity difference, you can also potentially imagine getting selectivity, right? So if you have a ketone and an ester and you only want to reduce the ketone, right, and you use sodium borohydride, you could selectively reduce one over the other. And we finished up last class with a mechanism, and we're not going to have time to go through all of this. But I just want to sort of restate that if you have, say, R2OH and water, sorry, and acid, say something like H2SO4, we will get molecules that look like this, right? Ketals, acetals. Really, the only difference between a ketal and an acetal is a ketone will come from a ketal, or a ketal will come from a ketone, and an acetal will come from an aldehyde. And I sort of also mentioned I'm not going to go over the mechanism because we don't have time for it, and I trust that you guys should all be able to figure this out on your own, right? That if you want to go in reverse, just add water, right? And so this is the idea that you can sort of go in a single direction through, sort of losing water, right? As we sort of discussed last class, and periodically throughout the semester you can go in reverse by adding water. Again, I'm not going to have time to go over this, but this is a reaction that you're responsible for, and previous videos and your book, you can also sort of see this as well. That if you were to take a carbonyl of some sort, and you were to treat it with, say, for example, an amine and some acid, abbreviate that as H+, the mechanism is the same, right? However, the difference is, unlike in the case of the carbonyl, in the case of the nitrogen, having that second hydrogen here, this is key. Will get you to a shift base or an imine. So you can, in essence, take a carbon-oxygen double bond, and you can convert it into a carbon-oxygen carbon-nitrogen double bond through the use of some primary amine. So that's key, right? And then likewise, you can do the reverse. And we're not going to have time to go over this mechanism, but it is exactly the same, right, is what we had seen last week with the ketals and the acetates. And so you're going to be responsible for learning this on your own. I'm not going to have time to go through it all. As you saw last week, these mechanisms are often very long. They take a lot of time, but you hopefully also realized that there was nothing special about any of these mechanisms. Once we're protonating, it's all sort of acid-base chemistry, nucleophile, electrophile chemistry. I'll show one example, just sort of reiterate this. Notice that this is the reaction if I did this with a primary amine, right? So where the nitrogen has 2 hydrogens on it. However, if we did the exact same reaction, but instead of with a primary amine, we had a secondary amine, meaning that there's only 1 proton. Right, so basically, have it R3, I'm just denoting it as R3 to separate it from the others, but there's 2 R3 groups, okay? And you went through the same mechanism. What's going to happen, right, is that, and this sort of explains the differences between these, right? If we were to do the condensation, went through all the mechanisms that we had previously, right? You're going to get to, and you should all be able to get to, the analogous intermediate that's going to look something like this. Right? So basically we'd protonate, and we'd add the amine in, and then we get a proton transfer. So it'd be 3 steps in terms of mechanisms. And at this point, what's going to happen, right, is these are going to kick down. And we're going to get this molecule called an iminium. Okay? And this is where it should make sense in many ways how a primary versus a secondary amine are going to go in 2 different ways. If instead of 2 R groups, based upon what we saw previously, we have that molecule there, how are we going to neutralize that amine? There's a very quick way that that amine can eventually be neutralized. Something that doesn't speak up that much. You see a lot of usual suspects. All right, go ahead. Yeah, so recognize the difference between this and this is the hydrogen. Hydrogen, we can easily do acid-base chemistry, right? And so if you have a primary amine, that's what you're going to end up getting as your intermediate. And again, you can refresh this by looking at the book or watching old videos of mine. Yeah, you can neutralize it in that way. Based upon the structure that I have here, we can't do that, right? That is not, well, I would say it's going to depend upon the nature. We haven't actually defined what R1 or R2 or R3 are. But by and large, when we're talking about getting, sometimes you can actually get to the aminiums and they'll stop. If you have no beta hydrogens, for example, to do this. But in general, you need some type of a beta hydrogen. So I'm going to move that away. I just changed that, so just be careful in your notebooks. I just added, so we have beta hydrogens. Just be careful if you were taking notes to recognize this change, because it's important. Given the fact that I now have beta protons, there's an alternative way that I can help that positive charge, right? And this goes back in many ways to elimination chemistry. You've seen this before, right? If we have beta hydrogen to, say, for example, a bromide, right? That's our leaving group. That's beta to that. And so we can do elimination chemistry, right? So we've seen before this idea of beta hydrogens, right, to a leaving group. In this case, we don't have a full leaving group, but we have something that's in many ways synonymous with that, right, Abraham? What's that? I don't know. You raise your hand, so yeah. Yeah, right. So we don't have a leaving group per se, but where we previously had a bond that would break to form the leaving group, as Abraham's saying, there's a resonance form that kind of can sort of help us see the same thing. We can put that positive charge there through the resonance form, but in fact we can do it in one shot. And the result of that is going to be that we're going to have a molecule like this. Remember enols? What an enol is? Right? It's an alkene connected to an alcohol, right? Enol. So the same type of name, this is an amine. So if this was an OH, right, that would be an enol. This has got a nitrogen there, so it's an enamine. Okay? Does that make sense? Okay. And again, the easy selectivity, I've just shown it in one form. It's going to be thermodynamically driven. So if, say, for example, your R3 was really, really bulky and your R2 was not so bulky, maybe it would go the other way. But again, that's just something to sort of recognize. Okay? All right. So that's just to show you that not all, that there are some subtle differences. Right? Okay, so this sort of all falls under the umbrella of condensation chemistry. And the remainder of today, and I think for the most part, all of the reactions that we've seen to date, and I get that some of them are really long, but they should all be fairly, once you see them, they should make sense, right? And yes, some of them are very steppy, and that might take a lot of focus and trying not to make mistakes to make sure that you can get through the whole mechanism. But I'm convinced that since all of you were able to get into organic chemistry too, that you should all have the skill set to be able to figure out those mechanisms. Through the mechanisms that we described earlier. I don't have time to go over it. So you have to look back at the old, it would be the same thing as the hydrates that we went earlier, right? Protonation, amine addition, proton transfer. So it's just too much, there's too many steps if we went over all the steps of all of them. But you're responsible for them. You're responsible for knowing that. All right. Okay, so all the other reactions, I think of all the reactions in the carbonyl chapter, the one that's maybe I don't want to say it's the most challenging, but one of the ones that maybe is a bit complex is the sort of the Wolff-Kishner reduction. Okay, so going back to reduction chemistry, right? If you think about our reductions that we've done, carbonyls, right? For the most part, what we've been talking about is adding, right? For the most part, what we've been talking about for reduction chemistry is the addition of hydrogen across that double bond, right? And usually the way that we're doing this, right, is with sodium borohydride or lithium aluminum hydride. You can, in fact, do this, and if you read your book, you'll see that you can, in fact, reduce carbonyls with hydrogen gas as well. I'm not going to go over that, but you guys should know that. That's in your book. But this is sort of, if we refer to what we talked about in terms of oxidation, you can have multiple levels of oxidation. You can also have multiple levels of reduction as well, right? And so while this alcohol wouldn't seem to be able to be oxidized anymore, right, technically if you can consider the loss of water, we can add another equivalent of hydrogen to this, right? So if this is plus H2, if we had another equivalent of H2 effectively across this, and again, I'm just talking purely hypothetical and bookkeeping right now to sort of explain the reduction phenomenon here. Right? you add that extra equivalent of hydrogen, you can imagine getting to a molecule where now you have water, right, bless you, and you fully reduced, right? So now we in fact have 2 hydrogens there. And so this is also a reduction. And there's a few classes of reductions that we have learned. And in fact, you can do this with hydrogen gas and certain metals, but the book doesn't discuss it. It's called protonalysis. But what the book does discuss is a couple types. One of which, the mechanism I'm not really going to discuss. The others of which I will. Okay? And so this would be called, now you can't reduce any further, right? So this would be called an exhaustive. Yeah. No. See, okay, so let me make this clear. I'm just showing you guys why it's considered a reduction. Yes, you can reduce an alcohol under extreme conditions with hydrogen and metal, but I'm going to teach you guys practical ways to do it. But I'm just trying to show you that much like in the case of an oxidation, we lost an equivalent of hydrogen, we lost another equivalent of hydrogen, that's kind of the oxidation. The reduction is adding an equivalent of hydrogen formally, adding another equivalent of hydrogen formally. So I'm talking about more just thinking about the bigger picture. But yes, you can do that, but I don't even think that's in the book. And it's usually depending on certain situations, usually it's harsh conditions. But the book discusses, I think, 2 classic examples to do exhaustive reductions. So exhaustive. And the first one, which again, I'm not going to go through the mechanism, and I'm not going to hold you guys responsible for this mechanism, but it's called the Clemmensen reduction. Okay. This is usually one that I don't spend too much time on because I think from a mechanistic standpoint we can rationalize the second one that I'll show you guys. But this is classic textbook reduction that is taught in virtually any organic chemistry textbook, and there's other ways to do this. But basically, a Clemmensen reduction is a metal-based reduction where basically you take this zinc mercury amalgam. That actually makes metal hydrides not too dissimilar to what we saw with like lithium aluminum hydride and so forth, but it's an even stronger reducing agent. The mercury in there also serves as a good Lewis acid to sort of help pull the oxygen, but don't worry about the mechanism too much. But it is a sort of a more hydride-like process. So know this reaction, know the reagents, know the product, in case it comes up in terms of like what is this reaction. But you won't get a question asking about the mechanism for this, so you don't need to know the mechanism of this. What you will not need to know the mechanism of is, I think, one of the more challenging mechanisms, and so I'll just show it up here and then I'll erase everything and we'll go over it, but it's the Wolff-Kishner reduction. Okay? And again, much like some of these others that we've seen in the past, the Wolff-Kishner reduction is going to be based largely on mechanisms that we've seen, but they do lead to some kind of interesting intermediates that might be a little bit perhaps counterintuitive, and so we'll discuss them. But the Wolff-Kishner reduction sometimes it's done in a single pot, but usually I think it's best to be taught as a 2-step reaction, so I'll teach it that way. The first reaction is you take hydrazine, so hydrazine is basically like ammonia sort of linked together, so NH2, where the nitrogens are bonded to each other. Hydrazine is a really, really, really good nucleophile for reasons that go beyond the sake of this, the point of this class. If you're curious about it, you can ask me afterwards. But it's the same way that sometimes peroxides are really good nucleophiles. When you have these sort of two lone pairs adjacent to one another, they have an effect that makes it strongly nucleophilic. And so you don't even necessarily need acid to get these to condense. In fact, you can actually do it under basic conditions. But I think just to stay standard to what we're used to doing, we'll just teach it with an acid in there, right? So that you can go through the mechanism. And if I were to take hydrazine under acidic conditions in a carbonyl, and I were to ask you guys, based upon what we just discussed, what the product would be, you guys should probably be able to tell me, right? It's not an exhaustive reduction yet. There's a second step to the exhaustive reduction, which we'll get to in a minute. So now, what do you think? If I were to take this and amine, yeah. Yeah, you'd have an aminium, right? You have the nitrogen. There's a second nitrogen there, but it would be an aminium. So, well, the aminium would be the positively charged version, eventually. But once it gets deprotonated, right, we have this. It has a name, I forget what the name is, but it's basically the imine version of the hydrazine. Again, I think the textbook gives it a name, I don't know what it is. It's an amine. It's a hydrazine-based amine. And then the second step of the Wolff-Kishner reduction, which again, you can actually do this all in one pot, but I think it's just easier to see it as two-step, and sometimes people do it as two-step. You treat this with a base. And this is the challenging mechanistic part that we'll go through together. But that's what ends up being the reagent that helps reduce this. And it's at that point that what you will get to is the exhaustive reduction. Okay? So Wolff-Kishner, hydrazine condensation in carbonyl to get the, I think it's like a hydrazide or something like that, but it's the sort of the imine version of the hydrazine, right? And you guys should all be able to do this mechanism, right? I'm not going to go over this part to it, but it's synonymous with everything that we've seen. You should be able to know this part. What I'm going to go over right now, I'm going to erase everything. I'm going to go over this latter part, how this sort of aminium here, under the presence of base, can actually fully reduce this, okay? Okay, now there's a number of different mechanisms that you can go through to do a Wolff-Kishner. I also find that there's one very highly simplifying first step. That if you can do this first step, if you can see this first step, it might make this mechanism a heck of a lot easier. Okay? And that is, oops. We have to get two hydrogens there. Is to recognize a relationship between the starting material and that molecule that I just drew. Yeah, give me a second. This molecule have a relationship between them that if you can see it, this mechanism is going to become a heck of a lot easier. Yeah. Okay, you're going through the mechanism to get there. I'm asking, how do these molecules relate to one another? There's a relationship between these two. Abraham, did you know it? You had your hand up? What is it? Well, okay, so you're basically just said the same thing that Arlene said. So you just said the same thing Arlene said. You got the mechanism of how you got from here to here. What I'm saying is that there's a relationship between these two. Kel. What's that? Well, they're isomers, yes, but more so than that. What's that? Yeah, say it louder. They're there, but this isn't a ketone or an enol. What's the next word? Tautomers, right? So the keto-enols are an example of tautomers. That's the analogy, right? These are not keto-enols, but that would be for a keto, ketone, and an enol, right? But this is the analogy of that, just with these molecules. So yeah, if this was a ketone, right? Let's just pretend that this is, say for example, an aldehyde, right? Where that's here, that carbon is the nitrogen, and that methyl group is that. Right, there's your enol. You guys see that? So now we've got a double bond there. We basically moved the hydrogen. So what is a tautomer? You know what the definition of a tautomer is? They're not resonance. Resonance would imply that you just have to move the electrons. Tautomers are a little bit more. Yeah. Kind of, part of it. But resonance could be explained by that as well. That could sometimes imply resonance as well. I mean, you look like you know it. You're going to pass on this one. So these bonds, Remy, you're half the way there. It's Rami, sorry. You're halfway there, right? The double bond moves, but what else moves? The hydrogen. So that's what makes a tautomer, right? It's the movement of it's basically two molecules that basically differ from one another based upon, in essence, the mechanism that was just brought up earlier by both Arlene, and Abraham brought up, which is simply deprotonate one place, resonate, reprotonate somewhere else. It's not a hydride shift per se. That's a little bit different. Hydride shifts are a little bit different. But hydride shifts can be forms of tautomers when you do a hydride shift. So hydride shifts can be a mechanism through which tautomers can form. This is just, you can do it with acid-base. It's not really the hydride per se. Okay, and then once you're here, if you recognize that you can move the proton there, and if you go through the mechanism and you deprotonate and you resonate and you reprotonate, you can get there as well. But these are simply tautomers of one another. And once you're at this tautomer, then the mechanism becomes a bit easier, right? Because now we recognize our reagent is sodium hydroxide. We got to find the acidic proton that the sodium hydroxide can react with, and there's really only one. I mean, we just put this here, so we probably don't want to go in reverse. Where's the one proton that the sodium hydroxide can react with? It's up here, right? And so if the hydroxide reacts, this is where the reaction is driven. This is where the part of the reaction that might be a bit, if you can get to this intermediate, the next step, although it's going to look on many ways difficult to wrap your head around, you can recognize why this reaction will be driven, right? What do we have to do here? That. So it's not a leaving group in the classic sense. Classic sense would basically say we want to go this way. It's going to leave in kind of the opposite sense. Yeah, Raquel. Oh, I guess this would be the leaving group, right? That would be your group. Yeah, so yes. Mark, you're right. It's a leaving group. This becomes your leaving group. Right? And you get to an intermediate that we ordinarily wouldn't want to show. I mean, if we thought about being in the gas phase, right, we probably would rather have a negative charge on a nitrogen than a carbon, right? Makes sense, right? We probably wouldn't want the negative charge on the carbon, right? We don't like having carbanions, right? We'd rather have that negative charge on the nitrogen. But why would this reaction proceed? Yeah. Not just that it's basic. I mean, the base is gone at this point. It's whether there's a negative charge here or here. And you guys should all recognize that negative charge on a carbon, more than not, is going to be less happy than a negative charge on a nitrogen. Obviously, there's changes to that. We've seen that, for example, with the acetylides, and we'll see it with ketones in terms of enol keto forms and generating enolates. But what do you guys think? Aisha, what do you think? What's that? Well, you have two R groups, but what's the byproduct of this reaction? What's that? N2. What's N2? Oh, you just said it. I thought I heard you say N2X. You said N2 gas. Yes, exactly. Right. So this is out of the atmosphere. Right. So I'll ask again. Why does this reaction go? Because you're generating nitrogen gas. And the nitrogen gas will leave the environment, rendering the process irreversible. So this is another example of Le Chatelier's principle, perhaps driving a reaction in a direction that we might ordinarily not feel like we would want it to go, but because we're pushing it into this direction because nitrogen leaves the equation, we're stuck back here with this, and now we got to protonate it. And we'll protonate it. In this case, we have the water that we generated over here, and in these cases, you guys could probably use the water. Regenerate the hydroxide you can get there. Right? And so, this is a bit different, right? As I said, it's a little bit of a different mechanism than what we've seen. And I think what makes it a little bit different is we've rarely seen mechanisms, for example, most of the mechanisms that we've seen invoke sort of acid-base, substitution elimination, and this is really no different. But I think the way that it's packaged might be a bit confusing. Again, you should all be able to get to that aminium or that imine formation, right? It's simply acid-base resonance polymerization to get to here, right? Right. So you should all be able to get to there just by protonation, deprotonation. Yeah. Draw this straight to the hydrogen? So I don't know. I would be okay with that. I'll be okay with that. It's risky in terms of making mistakes because you may be trying to do too much. But yeah, if you did that, I would be okay with that as long as you don't make mistakes. So the question was, could I avoid this intermediate and just have it grab the proton from the water? And I think I'm okay with that. Okay, any questions? Okay. All right, so... Okay, so we're almost done. Yeah.
What I remember about carbanions is that they're much more stable on primary and secondary. So if you had shapes and you have some kind of resonance going on, so
Oh yeah, so that's So if the R group was, say, for example, and we'll get to this. We probably won't get to it today, but we'll get to it maybe on Monday. If that was, say, for example, like a carbonyl or something like that. So certainly there are carbanions that through resonance stabilization, and even through alkynes, the acetylides, right? We've seen them be deprotonated. So it's not to say that all carbanions are less stable than amides, but most of them are. Right? All right, so All right, so I'm looking through this. I think we just have one more reaction, kinda. Before we get to enol keto. Okay, so that's a tricky reaction, somewhat from a mechanistic standpoint. Here's the other one that's a little bit tricky, but we'll try to reason it and understand it. And it's you know, to date we've only really learned we've really just kind of learned one type of carbon-carbon bond forming reaction, right? For the most part, right? Taking an alkyl lithium or an alkyl Grignard and treating it with a carbon-based electrophile, right? So generally, if we treat it with a carbonyl, if we take a Grignard, treat it with a carbonyl, take a Grignard, treat it with an epoxide, maybe take some of them, maybe you can get away with treating them with an alkyl halide, although sometimes that will be problematic. Acetylides, I guess, as well, right? Acetylides would be the better way to go about reacting with carbon-based electrophiles, but it's basically been carbon-based nucleophile reacting with carbon-based electrophile. And this is kind of in the vein as well, but it's a little bit more complicated because it's not necessarily as strong of a nucleophilic process, and it's a little bit more complicated. It's called a Wittig reaction. The other thing is all those ones that I just sort of stated to you, I think they all have in common is that you're making single bonds, right? It's making a carbon-carbon single bond. All of the ones that I just described had that. Wittig reaction is actually going to be a way to take a carbonyl and convert it to show it as substitutional positions. We'll sort of explain some of the reactivity behind the Wittig. But basically, the general idea is that we're going to replace a carbonyl with a carbon. Now, if you're trying to keep this reaction, and we'll get into some of the details of how you do this in a minute, but just in terms of an overall big picture that you would need, say, for example, for a synthesis problem, sometimes it's easy to relate multiple reactions together, right? And this is going to be a little bit different than much of what we've seen. But what we've done a lot in the last few days, right, is we've shown that reactions can go in a single direction, reactions can go in a reverse direction. How do we go? Do we know a reaction that can do this? Raquel, osmolysis. So one of the ways that you may be able to remember this reaction more generally is, hey, I know how to take an alkene to a carbonyl, right? Guess what? I could also take that same carbonyl and I can convert to an alkene, and in that way maybe you can try to keep this sort of organized in your toolbox of reactions to sort of pull from when you're thinking about synthesis or whatever. Now the reagent that we're going to use here is going to be what's called a Wittig ylid. So let me just spend a little time over here talking about the Wittig ylid and how we make it, and then we'll talk about the reactivity of it. We've seen triphenylphosphine a little bit in the past, right? So triphenylphosphine. Triphenylphosphine is simply a trialkyl phosphine molecule that's fairly stable to oxidations. A lot of the alkyl phosphines actually oxidize. So one of the special things about the triphenylphosphine is a little bit more stable, so it won't decompose as easily. Very important reagent. You look at the periodic table, you see that phosphine is below nitrogen, right? Recognize this has a set of lone pairs. It's also a good Lewis base. It's fairly nucleophilic, right? And so if you were to take triphenylphosphine and you were to react it with an alkyl halide, we'll just say here. right? And we were to treat it with that alkyl bromide that I just shown here. What's the product going to be? It's going to be a simple substitution reaction, right? The lone pairs on the phosphine. We're going to attack the bromine. Abbreviate with phenols, pH. What am I missing here? Positive charge, right, with phosphine. And what else am I missing? The bromide, right, so Br minus. So oftentimes when you buy, you can actually purchase what they call Wittig salts. And the Wittig salt is something like this. It doesn't always necessarily need to be bromide. Sometimes it's an iodide, sometimes it's a chloride. But usually you'll purchase a Wittig salt that will have some structure like this, right? And then what you do is you take that molecule and you treat it to some base. And there's numerous bases that people will use for this. The base that I'll tell you guys, I forget what the book says, but the base that I'm used to using, it worked pretty well for me when I used to run this, was potassium butoxide. It's strong, it's bulky, it's able to deprotonate this. It doesn't necessarily do anything bad. What that's going to do is that's going to deprotonate the hydrogen here, right? That's going to get to this molecule here, which is called an ylide. You guys heard the term ylide in the past? I don't know if you guys have. Ylide. So an ylide, Y-L-I-D-E, is a term referring to molecules, not resonance, not where you can say, for example, actually make the bond, although sometimes the Wittig ylide is presented in the resonance form as well, where you have a double bond there. I'm just going to keep it as the ylide, because that's actually more likely how it exists. But the idea here is that you have a negative charge and a positive charge on adjacent atoms, right? And this is what's called an ylide. And so there's several examples of this. This would be the Wittig ylide. Yes, right? So we're now in the 3 level. So now we can tap into the 3D, which is why like phosphoric acid, right, is a much higher, right? Right. So that's why you can make a double bond, right? Okay. All right. So if that's our reagent, let me make some space here. The way to sort of go about this, so first of all, I just want to sort of point out that the Wittig olefination is, I don't know what the latest status on the actual mechanism of it is, because there's been a lot of debate about it. But we'll go through it in a way that hopefully will rationalize it for you. And that's to basically take this molecule, which we had to deprotonate under fairly strong reagents, right? Sometimes you actually have to go stronger than the T-butoxide. And so this is fairly nucleophilic. And so it's best to, I think, first think about the Wittig as a nucleophile. And if it's going to react as a nucleophile with the carbonyl, how are we going to do that? Right, we're going to attack the carbon, push the electrons onto the carbonyl. Right, so that's going to be the first step. What we're going to be left with, which I'm going to kind of draw rather suggestively, is that molecule there. Now back to what Ronnie was just asking earlier, he said, is phosphorus one of those ones that can actually break the octet? And actually, you don't really need to break the octet rule here, but you do have to, sorry, there's 4 bonds to it already. I just had a little brain fart there. Yes, there's 4 bonds to it. We ordinarily don't like breaking the octet rule, but again, it's okay to break the octet rule on those third level, on those third row atoms, right? Because they're 3, you can sort of tap into the d electrons, you can sort of get these sort of hypervalent, right? So, with that being said, what can we do here? Should be fairly obvious. Somebody that hasn't talked yet. I'm in. Sitting there all quiet. Yes, I'm in. Your hands look like they're going in the right direction. So you're saying go here and then go here. All right, and what's that going to do? That's going to make a bond. Right, we're going to get to that intermediate there. Huh? Is that a Fisher projection? No, I mean, no. I guess it kind of looks like a Fisher projection. But no, it wasn't implying any stereochemistry, it was just drawn that way. And now we're a step away. Right, because we've seen previously that the phosphine was okay having that positive charge on it, even with the negative charge on the carbon, although that behaved as a nucleophile. But the oxygen could even more so take on the negative charge. And in fact, what you can do is you can basically eliminate in a way and lose triphenylphosphine oxide, right? Which, as I stated earlier, that one of the things about the phenols is that keeps it relatively stable. Over time, triphenylphosphine will actually oxidize with the air to triphenylphosphine oxide. So triphenylphosphine oxide is actually a more stable form of this. And so the triphenylphosphine oxide is favored, and it in part drives this reaction. And then you generate your double bond. Okay? Okay. So that's just a brief overview of the mechanism of the Wittig-Ullmann. But there's an additional, and that's a little bit different than what we've seen in the past, right? Already a little bit of a complicating reaction. We're making this wacky 4-membered ring structure here. Again, the first step, I think, should be easy for you guys. The second step, if you can sort of recognize, as the myth did, that we can sort of make that bond and break that. Perhaps the one maybe weird type of process is the generation of the triphenylphosphine oxide, but it's simply pushing a few arrows. Yeah, well, first of all, this is strain, right? So it's not very happy with the strain. And I'll get into some chemistry that may help explain this a little bit more in a second, but also triphenylphosphine oxide is a favored product, so that also helps drive the global equilibrium in this direction. Yeah? What's that? Okay. All right. So anyway, so back to some more complicating factors of the Wittig-Ullmann that actually make it valuable as well, right? Is that not only does the Wittig-Ullmann create double bonds, but as I've kind of drawn, right, I've really only drawn as a single isomer, right? I sort of have R1, R2, R3, R4, and I've simply drawn it with the R1 and the R3 on the same side, right, and the R2 and the R4 on the same side. And I just sort of drew that generically, but obviously, you know, I haven't really shown what it is, so R3 and R4 could be flipped, and, right, and so you can, in essence, get either isomers of these alkenes. And it turns out that the Wittig-Ullmann in general can actually have some selectivity for one or the other based upon what the source of the Wittig-Ullmann is. Okay? And so, in general, the rule is and then we'll try to rationalize this, right, is you can sort of know the selectivity based upon the quote-unquote stability of the illid. Well, how do we know that these are stability and rank stability of these? Well, I'll try to sort of help explain this to you guys. In general, when we're talking about an unstable illid, we're talking about the right, just to make things simple, I'll just put an H there. But basically what we're referring to here is cases where that anion that's formed isn't stabilized with anything else, right? So if that R group, what would be a way that that R group might stabilize a negative charge? Things like resonance, right? So specifically, and usually what people refer to here, just keep things simple, is they'll say if that group is, say, for example, a methyl group or some type of an alkyl group, or even a phenyl group or something like that, unstable illids I recognize this might confuse things because it's not as cut and dry as this, but we'll sort of stick with this just to help us understand it. But not capable of resonance stabilization. Again, this might cause confusion, but I'll be forgiving, I guess, in it, but I just sort of want to drill in the first point. These will lead to okay? So the general idea here is that if your anion is less stable, so unstable illid, less stable alkene. Okay, and I'll explain this in a minute. Space. More stable illids, like say for example if you had a ketone, and these are usually the classic examples that people give, right? Right? Let's say, for example, that you have a ketone there. Now you've got resonance stabilization. Okay? So less stable illid, less stable alkene. More stable illid, more stable alkene, okay? So if you can just memorize that, you'll be in good shape. But let's try to rationalize that, okay? So if you can remember more stable, less stable, less stable, that'll help you at least remember which one forms. But let's try to take it in another direction and try to understand this. And I've tried to go into a thorough explanation of this in the past, and I've just lost everybody, so I'm going to try to keep it as simple as possible. But if you have, let's change this and make this height. Let's give an exact example, right? So let's just say, let's make that a phenyl on the carbonyl. And let's make that a methyl group, okay? And so what would that alkene come from? That alkene would be basically the ethyl bromo version of the vitigillin, right? So we have right? So that's going to be our first intermediate. Again, I've tried to explain this in the past, but basically the take-home lesson is that the approach, and I can try to explain this You know what? Why not? I'll explain it this way. Okay, if we were to actually have this ILLIT approach, right? It would sort of approach in a method where, you know, we're not too dissimilar from, say, for example, it's not going to be all that different from, for example, if we're looking at sort of a Newman projection, right? The thing, and the reason why this isn't complete, I'm almost going to give you an old school explanation that's actually been disproven, but at least can rationalize it for you guys. But if the phosphorus ILLIT were going to attack this group in this fashion, and what you have to sort of realize to do this, or what you, the leap that you have to take, is to have the phenyl group be opposite to the carbonyl in order for this to work, which is not necessarily true. But if I were to do this, now we're going to have to put a methyl group one place and a proton at the other place. What would I do? Thinking back to our Newmans. I want to put the methyl group over here, right? Right? And if we attack in this fashion, and I drew our sort of Newman projection, we would get a molecule like this, right? And when I told you guys, but what we showed previously is that the phenyl needs to actually overlap with the oxygen, right, to make that four-membered ring. So what we want to do is we want to rotate around. Just going to draw the offset so that you can see this a little bit better. But to sort of wrap that around and get to this intermediate that you see right here, what can I just do? Right? When I rotate this around, which place does the methyl group end up at? Over here, right? And where does the proton end up? All right? Such that when we do our elimination, right, what's the product going to be? They're going to be on the same side of it. So let's just walk through this one more time, right? The tough part that's a little bit counterintuitive for reasons that are perhaps accurate, this is a classic explanation of the stereochemistry, which isn't entirely accurate. So, but it helps explain this, is that the approach, you have to sort of reason that the approach is with the phenyl being opposite of the carbonyl. If you assume that that's the kinetic approach, you're going to get to this intermediate here. When you rotate around, that's going to put the two groups on the same face as one another, and it's going to do an elimination. Okay? This is assuming that this is not reversible. Okay? What this implies, right, is at the moment that you get to this intermediate, it can't go back. If this is unstable, right? If this is unstable, once this attacks, it's probably not going to be reversible. So its only pathway is to go forward. Does that make sense? Right? However, if this was, say for example, reversible or stable, then now maybe this is reversible. And if this is reversible, then over time what's going to happen, right, is that that methyl group at some point is going to end up over here. Right? Now when it rotates around, we're not as high, now we're not having this eclipsing interaction here, right? So actually at this point, it's lower in energy. right? And now what's the result? Is Z. So, sorry, it's opposite, it's E, okay? So, again, I get this is a little confusing, so I'll just try to reiterate it one more time. Summarize. If this first step is not reversible, it has only one choice to go through, and that's to the sort of the non-stable Z product. If it's stable, this is now reversible, so even though this product here might have been higher energy, it's reversible, so eventually it can access this form, and it turns out that that intermediate, now you don't have to have the two groups eclipsing one another, so you can go to the Z. So I get that's a little bit more confusing, and the most important point of this, though, is the recognition that certain Wittig-Ilids will give you E, and certain Ilids will give you Z. Okay? Stable, stable alkene. Stable Ilid, stable alkene. Unstable Ilid, unstable alkene. Got it? All right. All right. So looking at my notes, there is one additional reaction that we didn't touch on. It's not really I mean, it's an important one, but I feel like it's usually discussed in the imine chapter, but I'll discuss it here. And that's reductive amination. Okay. It's all a reductive amination. So it's a reaction from carbonyls that should make total sense to you guys. What's the first step? I heard it somewhere, I think. I take a carbonyl, I treat it with an amine. What's that? Aminium or the imine. Right? I've got sodium cyanoborohydride. What do you think sodium cyanoborohydride is? It's just kind of like sodium borohydride. Sometimes I haven't even taught sodium cyanoborohydride. It's got a little bit different reactivity profile, so it's been optimized for iminium reduction. But yeah, you just sort of, the first step is just condensation, second step. And again, we'll probably come back to this once we get to the amines, because it turns out that this is a good way if you want to make, for example, primary amines, because making amines from nitrogen and alkyl halides can be sort of challenging. All right. The second step, it would just be the hydridation line. It's kind of like what we talked about. That's fine. All right, so we don't have too much time, but that's everything for the carbonyl chapter. It's kind of dense because there's a lot of condensation chemistry, and we just sort of glanced over them, but you're responsible for all the mechanisms of all these different things. The one that I said that you're not responsible for is the Clemmensen reduction. But again, be prepared for these. The other thing that you guys have to start doing, and it's going to come up, I know that we had quiz 1 this week, or some of you are having quiz 1 this week. Next week, you guys are going to actually, and certainly on the exam that's coming up quickly, you guys should be perhaps continuously keeping on top of synthesis, right? So synthesis, I just sort of gasped somewhere, or was something wrong? Oh, that was you. So again, we're not going to spend too much time in class going over synthesis. I will dabble in synthesis when we have some free time, but you guys should all be practicing synthesis. This should be something that you guys are getting good at. And in the last several minutes, I will throw up a synthesis problem, and we will try to go over it together. I'm trying to come up with one off the top of my head right now. So, we don't really know how to do stereochemistry here, so you'll likely get a mixture. Although we can perhaps propose stereochemistry, which we'll get to depending upon the type of synthesis that you guys are doing. Here's a synthesis problem. It involves creating water and methanol. I guess you kind of are adding water and methanol, but you're also kind of, I guess technically overall you're adding water and methanol, but yeah, you're not just adding water, or sorry, you're not just adding methanol or water. All right, so what do we think? Again, there's a couple different ways that we can go about doing this, but one of the ways that might simplify this problem right off the bat, could be retrosynthesis. And so we've talked about retrosynthesis a little bit. It's a very valuable technique that could be useful for you. Sometimes it's difficult to say, hey, how do I want to go from here to here? Sometimes it's a little bit easier to say go in reverse. And when you look at that product that we've seen, where we had to make a carbon-carbon bond, and we have left behind an alcohol, what might be a type of reaction that you'd want to use to make that, and what would be the retron? Right? What might be a reasonable retron right away where we could actually create that carbon-carbon bond? Abraham. Yeah. No. So, well, no, we're doing retrosynthesis. So how do we make that? We got to have that on there. Oh, you want to hydrate it. Oh, you want to, okay, I think I see what you want to go to this. That could be a retron. That wasn't the one I was thinking, but yeah, that's, so how would we, so basically, if we added acid and water, that might be one way that we can do that. The problem with that, though, is we've missed out on an opportunity to create a carbon-carbon bond, right? We don't know ways to make this carbon-carbon bond yet. We will later on in the semester, but at this time, we don't know how to make an alkene. Well, maybe we do. So, okay, so maybe this would be one way, but given the time, I think there's a simpler way to do it. So this would be one retron, and you are correct. But now we have to figure out how to make one of these bonds, and I'm imagining that you could do that, but it would be steppy. So there could be a way this route, but it's not necessarily the route that I was thinking. Yeah.
We treated like some kind of
Right, so a Grignard, that's actually what I was thinking. Because now we've got our opportunity to make our carbon-carbon bond. I think that's the more general point that I wanted to make, is that when we have an opportunity, when we're doing a retron, to actually do the carbon-carbon bond, we'll want to do that. And what would be the Grignard treated with, Rami? Rami, what would be the retron? Well, the retron. Well, yeah, that's one retron. But what would be our other one? No. What would be if we took this? If this reacted with something to make this, what would that be? Carbonyl. Carbonyl, right. Right? So, again, we know that we can take Grignards, we can treat them to carbonyls, and we can generate molecules that look something like this, right? All right, so now what we need to do is we need to somehow get an oxygen up here, right? And we need to, we also need to get it in the right oxidation state. So which one do you feel like, I mean, both of those could be the same thing and they could lead to the same answer, but yeah. Right, so if you want to put an oxygen there, we know that we can do that, right? We use sort of BH3 hydrogenation, right? Right? And then what's the product? Then what do we got? How do we go from here to here? Any number of things, right? BCC. Well, acid would lead us in the reverse direction. PCC, Jones reagent, Swern, any number of these oxidation conditions. So I'll just put down PCC. Okay? And so this is going to be the level of difficulty. I'm going to think of three, when I put together your guys' quizzes for next week, I'm going to think of three reactions. I'm going to think of syntheses that would take 3 steps to do. It's okay if you spend more than that, but if you find yourself doing 8, 9, 10 steps and you're still not quite there, you might want to start over and realize there's probably a simpler way to go about doing it. But I will accept any answer if it's right. The problem is that if you guys have too many steps, the more steps that you have, your penalty is you're more likely to make mistakes, and you've just spent more time. So you want to get efficient, and you want to come up with the best synthesis, but I'm not necessarily going to penalize you. You effectively penalize yourself. So, okay? All right. See you next week.